So here's the theorem. You need a field. So if f is a field and n is a non-negative integer, then a polynomial of degree n in the field of polynomial field has at most n roots in that field. So that's the theorem that you're quoting when you're grading and you know something seriously has gone wrong. Some of you are smiling at me, so you know that you've gotten 3 roots sometimes for a second degree polynomial.
Normally you don't get enough. That's
right, that's true.
So you said something with rings that's different.
Yeah, it's rings. You don't. It's not different. You don't have that nice theorem.
You don't have any kind of restrictions necessarily.
You might have something. You might have something to do with factorization and divisibility. You might have something like that.
So just going back, that the point is, if it's an integral domain, you won't get n roots for an n.
What every finite, I was going to prove it for you for this time because I wanted to show you. It was demonstrated to me that I need to show some more proofs because I'm kind of stepping off of proofs. I need to go back to the basics and show. And I was going to show you the proof that integral domains that are finite are always going to be fields. So for a finite integral domain, you're always going to have a field. But in the case of infinite ones, you don't have that. Right? You have at most, right? And that's why sometimes you could have a complex root over the field of R, which you would need to extend the space. When you get exactly, well, you're in the right field. You're in an algebraically closed field. So that's when you get exactly. So if you have a field and a non-constant polynomial, we call that non-constant polynomial irreducible in the polynomial field, provided that p of x cannot be factored as a product of 2 polynomials in that polynomial field. So you can't factor it the way we factored. I had you just do some computations to factor so you know what I'm talking about. I call these things checkability theorems because you sometimes have to prove, in fact, often on the comps, it's the easy one to ask for me, just prove that this is irreducible. So how do you prove something's irreducible? Well, if you have a polynomial that's bigger in degree 2, it's irreducible. If it's irreducible, then it has no roots in f. So let's suppose I asked a question, is this polynomial irreducible or not? One quick thing you could do is check if it has roots. And if it does have roots, the answer is no, right away. If you're in the case of degree 2 or 3, and the polynomial, it's an if and only if. If you have a polynomial that has no roots in the field, then p of x is irreducible. So if I give a 3rd degree polynomial on a comp and say ask if it's irreducible, you can definitely answer that question by checking for roots. If I ask it over Z5, you can quickly check if it, right? I call this doesn't have a clue question, because if it's so quick, if they don't know what to do, they don't know the definition of irreducible, they don't know the definition of root, they have missed a fundamental understanding of something. So let's look at x cubed plus x plus 1 in Z2. It's got no roots in Z2. How can I check that? I check that by just plugging in the vast amount of values in Z2, which is 0 and 1. And if I plug in 0, I get 1 as a final result, and if I plug in 1, I get 1 as a final result. So therefore, by the checkability theorem I just gave you, this polynomial is irreducible. So I'm going to show you a different example because I wanted you to take this one and do some of the similar calculations to it that I'm doing with this other one. X squared plus x plus 1 has a similar problem. It's irreducible as well, because if I plug in 1, I get 1 as a result. So by the same checkability theorem, this polynomial is also irreducible in Z2. So you can ask yourself, what is the simple field extension for this root? And I bring this up because this was my first real taste of algebra. When I got to Montclair State, back a long time ago, and I was assigned the abstract algebra course to teach. I'd never taken abstract algebra, so I was going by the book and learning everything as I was going along. But then I started thinking about one of the problems I was working on, and I thought, man, it kind of feels like some of the stuff I'm doing in abstract algebra. And I went to John Stevens, which unfortunately I think he got ill before your time, so he's not here. He's no longer here. Did any of you have courses from John Stevens? Nobody? It's a shame. Genius. He has one of these going around his head. He's one of the most brilliant researchers that ever stepped foot in this department. But I came to him because he not only worked on engines at Toyota, but he has his degree in abstract algebra. So this guy could do everything. And he said, I think this problem has something to do with abstract algebra. So he began teaching me abstract algebra from his point of view. One of the first things he did was talk to me about a polynomial like this in Z2. And he said, let alpha be the root. And I asked him, well, what is alpha? If alpha is the root, what is alpha? I kept asking him, what is alpha? Because I wanted him to say alpha is square root of 2, or alpha is 3, or something. And he said, alpha is alpha, just alpha. So it took me a long time to understand that he has no number symbol for alpha. It is a root, which this is a representation of that root. So the first step in figuring out how you're going to form the simple group, the simple field extension, is to actually look in Z2 of alpha and see what is in there. By the theorem I gave you, I think last time we met, you know that the simple field extension is going to look like this. It's going to be all combinations of A plus B alpha, where A and B are both in Z2. Well, I literally can write that out. And John Stevens did something like this. And I would just point and say, but what is this alpha? And he would say again, louder, alpha is alpha. But I was expecting a number. So that's what this thing is. What's nice about Z2 and why I love Z2 is I can't make a sign error in Z2. So the first thing you do, I make a sign error all the time in other classes, but if I'm working in Z2, if I taught a class in Z2, I probably wouldn't make a mistake all semester long. So if you look at alpha squared, I can figure out what alpha squared is because it's the root of the polynomial, and alpha squared turns out to be minus alpha minus 1, but minuses and pluses are the same in Z2, so it's alpha plus 1. So the second step in determining what this field looks like is to look at all possible powers. If I go to the next power, alpha cubed, I don't get anything new. I don't get new stuff. Alpha cubed turns out to just be 1. So alpha squared is the first new object I have. So now I make my Cayley table. The plus, well, I just set up the Cayley table with 0, 1, alpha, and alpha plus 1. Those are the elements of my new field. I know this stuff, easy stuff. How do I get those things? Well, 0 plus alpha is going to be alpha, so those things come from the identity, so they stay the same. In here, alpha plus 1, well, alpha plus 1 is one of the elements in my simple field extension. So I put those in. Alpha plus 1, well, that's alpha plus 2, which is alpha plus 0, which is alpha. So this guy over here I get just by adding mod 2, so that I don't get anything too interesting there. And the last bit I get 0, 1, 1, 0. You can almost see it's screaming for a reduction. You can see it the way I've drawn it here. So this is what the addition table looks like. Good? Makes clear sense? Then we do the multiplication table. In the multiplication table, I need the fact that alpha squared is alpha plus 1. That's the easy part. Right? 0 times anything is 0, so all those get put to 0. 1 times anything is itself, so those all become itself. Alpha times alpha is alpha squared, which is alpha plus 1. That's where that comes from. Alpha times alpha plus 1 is alpha squared plus alpha, but alpha squared is alpha plus 1. So I get alpha plus 1 plus alpha, which is 1, because alpha plus alpha is 2 alpha, which is 0. So I get 1s here. And then the last one is alpha plus 1 squared, which turns out to be alpha. How do I get that? Well, it's commutative, so I can apply the FOIL that you apply for high school teaching. You get alpha squared plus 2 alpha plus 1. This drops out. I get alpha squared plus 1, but alpha squared is alpha plus 1, and then these two add up to be 0, so I just get alpha. And that's how you formulate the multiplication table. So I actually really recommend that you, I don't know what I put for the in-class assignment. I put something in Z5. The cubic that I gave you, or the square I gave, or the cubic I gave you earlier, right? You showed that it was irreducible. I would recommend doing the same kind of calculation. I found out last time I taught abstract algebra, I just gave this kind of a problem just in memory of John Stevens. And I felt like students really started to understand what these simple field extensions were, or what a field extension was, what was happening as they actually formulated these tables. I'm going to have you do the Z5 one, so you can try it out. It's not as bad as it looks. So I'd like you to try that one so you can get a full understanding. But these are beautiful computational problems that you can do where you get a really good understanding.
There's 25 elements.
5 and 6.
Right?
Is there?
Number 4.
For number 4?
For number 5.
There's 25 elements you found?
They're here now.
Maybe.
Okay.